Hi, folks, and welcome to this session at the ARM Dev Summit. So today I'm going to talk to you about building cloud-native applications on AWS with our Gravidon2 based instances. I'm Arthur Petitpierre, a senior specialist solution architect focusing on AWS EC2 Gravidon2 based instances. We are going to start with a deep dive on AWS Gravidon2 based instances. As you might be aware, AWS is a pretty broad platform with a super large number of compute instance type. We have more than 275 different instance types that span across many different categories. We have instances that are general purposes. We have burstable instances. We have instances for compute-intensive workloads, for storage, for super dense storage, instances with GPUs, and instances with graphic cards for graphic-related workloads. All those instances came in different forms and shapes with a choice on the processor type, with different types of processors, some being faster than the others, and with more or less memory, some instances with up to 12 terabytes of memory, and lots of different options. Historically, we've started our cloud journey with instances mainly leveraging Intel-based CPU. Later on our cloud journey, we added AMD-based instances, and lately we've been starting to add AWS-designed processors, the Gravidon processors, to our portfolio of instances. And today we are going to deep dive on those instances and show the benefit that they can bring to customers. We first introduced the Gravidon processors in 2018 with the A1 instance that was featuring the first generation of the Gravidon processor. That was the first processor based on the ARM architecture that would be available on AWS, and we made it a first-class citizen on EC2. It was a processor based on a 16 nanometer manufacturing technology with 5 billion transistors. The next generation of AWS ARM-based processor is called the Gravidon2 processor, and we released it at reInvent in 2019, and is a completely different beast compared to our first generation. That new version of the Gravidon processor has 4 times more vCPUs. The first generation had 16, that generation has 64, which brings an overall 7 times more CPU performance. We, on a single thread basis, we have twice the performance per vCPU. The processor itself is built using a more modern manufacturing technology, using 7 nanometer, and that's the first 7 nanometer chip to be available on EC2. And it's a way bigger processor. It has 30 billion transistors compared to the 5 billion we had on the first generation. Digging a little bit more into the cores of the Gravidon2, we can see that they are built using the ARM Neoverse N1 architecture, which is an ARM v8.2 compliant design. And actually, AWS worked closely with ARM on the creation of the N1 core design. We ensured that it would provide a large amount of L1 and L2 cache per vCPU for application to run super efficiently. We made it super efficient as far as overheads of interrupts are concerned. A server workload is pretty intensive as far as handling the interrupts is concerned. We ensured that it would handle virtualization in a pretty efficient way, and that it would handle context switching very fast, given that on a server, you tend to have many processes running at the same time, and you have to handle the parallelism of those workloads. It also features dual SIMD units for efficient vectorization of workloads. And it supports specific data types that are targeting at accelerating ML inference, like int8 and FP16. One of the things that is specific to the Gravidon2 processor on AWS instances is that every vCPU on that processor is a physical core. On most of our other instances, every vCPU is actually an hyperthread, and two hyperthreads are mapped to the same single physical core. On the Gravidon2 processor, on the contrary, every vCPU is a physical core, which means less concerns about security issue involving reading the cache from an other hyperthread, and it's a good benefit for customers. At the interconnect level, the Gravidon2 processor features 64 cores connected together with a mesh, and that mesh provides 2 terabytes of bisection bandwidth. It also has 32 megabytes of last level cache, and something really important for application developer is that the topology of that processor is almost flat. There's no NUMA concern. From every core, you see the same path to the memory and the same path to the other cores, which means that, for example, if you're developing a database, you don't have to take into account at the design level where you are allocating the memory. The memory is going to appear as almost flat to your application. It also features a large number of PCI Express Gen 4 lines to provide a lot of flexibility as far as the instance configuration is concerned, so that we can implement instances with a large amount of network bandwidth, instances with local disks. If we look at the different families in the Gravidon2 based instances, we have 3 general purpose instances, the M6G, C6G, and R6G instances that are shaped in a similar way to our existing x86 based instances, respectively M5, C5, and R5. And those instances are 20% cheaper on a per vCPU basis, and they tend to be faster for most workload. So from a price performance standpoint, we tend to say that they are up to 40% better than our equivalent Intel-based instances. We also introduced the T4G instances, which are burstable general purpose instances with a similar model to our T3 and T3A instances. They're well suited for spiky workloads on which you might benefit from the ability to spike some additional CPU cycle for time to time. All those instances are available now, and for the M6G, C6G, and R6G, they have variants with local NVMe-based SSDs. They're called M6GD, C6GD, and R6GD. And they provide application developers with alternatives with a local fast SSD that can handle application that would be that would need very fast local disks. The M, C, and R families also have bare metal options, which are sizes in those family where we removed the hypervisor thanks to the benefit of the Nitro platform, so that you can run an operating system directly on the processor without an hypervisor in the middle, which allows to access directly the performance counter, and if needed, it allows you to run your own virtualization system. If we look into the details, and we are going to start with the M6G instances. M6G instances are available from medium size up to 16x large sizes, which means from 1 to 64 vCPUs, and they have 4 gigabytes of memory per vCPU. From a networking standpoint, they offer up to 25 gigabits of bandwidth. And from a virtual disk bandwidth standpoint for our EBS volumes, you can get up to 19 gigabit per second. On the C6G instances, the only difference is the amount of memory per vCPU that you will get. On the M6G, you would get 4 gigabytes of memory per core. On the C6G, on the contrary, you get 2 gigabytes. As far as the network or the EBS bandwidth is concerned, that's exactly the same system, and it would behave the same way. Now, if we look at the R6G instances, again, the only difference is the amount of memory you get per vCPU. You get 8 gigabytes of memory per vCPU. And all those instances are now available in US East and in Ohio, in Oregon, in 2 regions in Europe, Ireland and Frankfurt, and in 4 regions in Asia, Mumbai, Singapore, Sydney, and Tokyo. And we have plans to roll them very soon in an additional number of regions. All those instances also have variants with local disks, and you can see that you can get from almost 60 gigabytes of local disk up to twice, almost 2 terabytes of disk per instances. Now, if we look at the T4G instances, so our burstable instances, you can get them in different sizes, starting from 2 vCPUs and half a gigabyte of memory, and you can get up to 8 vCPUs with 32 gigabytes of memory. Now let's have a look at the software ecosystem on the Gravidon2 based instances. Those instances are going to mainly run open source based operating system, be it Linux or FreeBSD or NetBSD. All the major Linux distributions are supported. Amazon Linux too, obviously has received lots of attention from AWS. We've ensured that it's well optimized and that it would run perfectly well on ARM64 based instances. The LSE extensions are supported both at the kernel level and at the glibc level. Ubuntu is also an excellent option to run on AWS Gravidon2 based instances. The 2004 version has now support for LSE in the glibc by default, and it's going to be backported to 1804 soon. And if you prefer to run SUSE or Red Hat, that's also an option. On Red Hat, you have to run at least the 8.2 version, and that would be the same for CentOS. As far as the container ecosystem is concerned, the Gravidon2 based instances are perfectly supported for Docker. You can both generate containers on Gravidon2 based instances. You can run container-based workload using the two managed services for container orchestration on AWS, using either Amazon ECS or Amazon EKS, which is the Amazon version of a managed Kubernetes. And you can also store container images on Amazon ECR, which is able to store, which is multi-arch enable, which means that it is able to store two versions of a container for two different architecture under the same tag. So you can build a container image for both x86 and ARM64 and then push it to Amazon ECR under the same tag. We also support Firecracker on Gravidon2 based instances. It is a micro VM that we use to run Lambda and Fargate. Lambda is not yet available on Gravidon2 based instances, but that's something that might happen in the future. And Bottle Rocket, which is an AWS supported open source project, which means at implementing a container-based operating system. So an operating system that would be specifically tuned to run container workloads in a secured and efficient way. And Bottle Rocket support ARM64 and the Gravidon2 based instances right from the beginning. In terms of tooling and software, most of the software released by AWS or supported on Gravidon2 based instances, be it the different software agents that are useful to run on EC2 instances. I would take, for example, AWS Systems Manager that allows you to connect to your instances without the need for SSH. Amazon CloudWatch Agent is also available and allows you to forward logs and metrics to the Amazon CloudWatch managed service. The Amazon Inspector Agent, which allows you to scan for security issues on EC2 instances, is available for the Gravidon2 based instances. And we start to have a couple managed services to be available on EC2 instances also. AWS Batch is such an example. It's very convenient to run batch workloads on AWS. The different development-related services are also supported on Gravidon2 based instances. For example, Code Build, Code Commit, and Code Pipeline. And last but not least, Amazon Corretto, which is the AWS supported version of a GVM, is available on Gravidon2 based instances. And we have a team that is working on improving it and optimizing it specifically for ARM64. In terms of the software ecosystem on the Gravidon2 based instances, there's definitely a momentum of software vendors adopting the ARM64 architecture and releasing their software for the Gravidon2 based instances. There's a very dynamic landscape of CI/CD tools that have been ported to AWS and the Gravidon2 based instances. For example, Jenkins supports the Gravidon2 based instances, so you can run your build pipelines and your tests on Gravidon2 based instances. In the configuration landscape, Chef is now fully available, and you can download pre-built binaries for the ARM64 architecture that would run on Gravidon2 based instances. In the security domain, people like CrowdStrike have announced support for Gravidon2 based instances since their release. So if you need a security system to scan your ARM64 based instances on AWS, that's definitely an option. And the list is growing. Many software vendors are now adopting the platform and offering their software to run on Graviton2 based instances. Now we are going to have a look at what it means to be running a CI/CD pipeline on ARM64 to build and deploy an application in the cloud. So the release process for a modern application in the cloud is usually the following. You start with the source. You check in your source code, such as Java files or Python files or C or C++ files into a source code repository. Your developers are going to do peer reviews and finally accept to check in the code. And that's going to trigger a build process. It means that it's going to compile the code, most probably run unit tests, potentially run style checkers. And then once all the code has been compiled and unit tested, it will create container images and or functions to deploy the different packages. The next step is usually to run integration tests with other systems, potentially load testing, potentially up to UI testing and security testing. And then once all the tests have been done, it's going to deploy to production environment where the newly deployed environment are going to be monitored so that in case of errors or problem, the environment could be quickly rolled back. Now, how does it looks like when using the AWS tools? So there are several managed services available on AWS to run the different parts of such a pipeline. The first thing is AWS Code Commit. AWS Code Commit is a managed version of Git that allows you to manage your source code, get it versioned, and trigger build process whenever a new piece of source code is committed to it. The next piece is the build system. You can build on AWS using AWS Code Build, which is a build service that's going to allow you to build code on the different architectures that are available on AWS. AWS Code Build is able to build both for ARM64 instances and for x86 instances. So you can use it to build a multi-arch application. Then you can keep on using Code Build to run the tests or add also third-party application to do that. And finally, AWS Code Deploy is going to help you to deploy the binaries or the containers to your test and production environment. When it comes to monitoring application, you can use AWS X-Ray, which is a framework to collect traces and analyze traces from your applications. And you can also use AWS CloudWatch, which is a monitoring managed service that allows you to collect the logs and the metrics from your instances. How to apply Code Build to ARM64 builds. So AWS Code Build supports building ARM64 binaries. And to do that, the first step is to create a build project. And in that build project, you're going to have two choices. You can either choose to use an Amazon managed image, in which case it's going to be super simple. You just select AWS/codebuild/Amazon Linux 2-ARCH64 standard, and an ARM64 build is going to be triggered automatically. Or you have the additional option to use a custom image in case you would have some specific requirements as far as the container that you are going to use is concerned. And in this case, you need to go to the additional step of selecting ARM as the environment type. And in both cases, the builds are going to be run on an 8 vCPU instance with 16 gigabytes of memory, which should be sufficient for most of the build jobs. Let's now have a look on how you can leverage AWS container environments like ECS or EKS to orchestrate applications on ARM64-based instances. In this specific case, we will talk about an application that we will transition from x86 to ARM64. Before going to that, let's have a quick look at what the AWS container services landscape looked like. So at the management level, which is where you deploy, you schedule, and you scale your containerized application, you have two main options. On one side, you can use Amazon Elastic Container Service, which is AWS specific version of a container orchestrator, or you can leverage Amazon EKS, which is a managed version of a Kubernetes environment. As far as hosting is concerned, there are two options. The containers can either run directly on Amazon EC2 instances, or they can run on Fargate, which is a 100% serverless service provided by AWS, where you just have to manage the containers. And finally, you can host your container images on AWS using Amazon Elastic Container Registry, which has multi-arch capabilities. So you can store a multi-arch version of your containers potentially under the same tag. As far as the ARM64 architecture is concerned, as I said, Amazon ECS and EKS are fully supported. Amazon ECR supports multi-architecture manifest files. And there's a blog post on our website that you can have a look to if you want to know more details about it. Amazon Code Build can be utilized to build images for Graviton2 instances. And Docker itself also has a multi-arch toolchain to build ARM64-based containers through a tool called BuildX. Now, let's look at a real use case. So I'm going to present here an application, a web application that sits behind a load balancer on an ECS cluster. And we are going to go through the different steps that uses a blue-green deployment process to migrate an existing application from x86 to ARM64. So the initial stage is that we have the application sitting behind the application load balancer, behind a target group, fully provisioned with x86 instances. Our first step is that we are going to add to our application load balancer a new traffic listener on a different port that would be redirected to a new target group. The next step is that we are going to provision new ARM64-based instances behind that target group. And once those instances are going to be provisioned, we are going to start redirecting part of the traffic to that new traffic listener. And so part of the the traffic from the application is going to be redirected to those ARM64 based instances. If all our monitoring look okay and the tests are good, we can now decide to switch the production traffic to those new pods, and so that it would run on ARM64. And once it runs successfully, we can start to drain the existing x86 instances to have all our traffic now running on our ARM64 based Gravidon2 instances. As a conclusion, running applications on EC2, M6G, C6G, or 6G, or T4G instances using the Gravidon2 processors can provide you up to 40% higher price performance compared to our x86-based instances. Those instances are available to be used on many different types of workloads, from application servers, open source database, up to high performance computing or video encoding. Most of the Linux distribution and the open source application are well supported on ARM64, so they are perfectly well suited to run on those instances. And finally, all those instances are available now, so you can leverage them in your applications and your deployments. Thanks a lot for attending this session, and I wish you an excellent ARM Dev Summit.